So I think we should start. The session is begin. It's 7 already. So we'll start with today's session. So in today's session we'll be covering few of the topics. So we'll start with atmospheric water. Like what is atmospheric water? If you can see, my screen is visible. So we'll talk about atmospheric water first. Then we'll cover 5 definitions. Once we know what is atmospheric water and how it is happening, then we'll cover 5 definitions. So those definitions are, we'll talk about vapor pressure, we'll talk about specific humidity, we'll talk about relative humidity, we'll talk about dew point temperature, and we'll talk about saturated vapor pressure, ESAT. So once we are familiar with atmospheric water, we'll cover this 5 definitions, and also we'll try to do some few of the derivations so that we can remember this definition as well. So in today's class there will be like around 18 to we'll be deriving 18 to 12 derivations or equations. So this is the first part of today's session. We'll talk about atmospheric water followed by these 5 definitions. Later we'll talk about how atmospheric water or water vapor inside a column. So here we'll derive few relations of pressure versus altitude. We would like to see like how pressure changes with respect to altitude, whether it increases or it decreases. So we'll derive a relation between pressure and altitude, and at the same time we'll derive a relation between temperature and altitude as well. So if you have already solved the assignment, you will see there were some certain numericals that I've asked and that are based on this concept. So this will be the second part of our session today. We'll talk about the relation between pressure and altitude and temperature and altitude. So this will be the second part. Once we are done with this, we'll talk about what is precipitable water, and also we'll talk about how precipitation takes place. So we'll talk about this. So this will be the third part of today's session, and finally we'll conclude the session with a derivation of terminal velocity. So these are the topic that we are supposed to cover in today's session, and once we have covered all this concept and derivations, then I think it will be helpful for you to solve the assignment. So let us start with the first part, which is atmospheric water. So in the previous class we have studied about like how hydrology is divided into 3 parts, right? So the first part was atmospheric water itself. So in this lecture we are going to study more into atmospheric water. So we know, like when we talk about atmospheric water, we can say that the water exists in atmosphere in 3 states, in all the 3 forms. So if we talk about atmospheric water, we are saying it as AW. So atmospheric water can be present in either of the 3 forms, which is, it can be present in the form of gas, or it can be present in the form of liquid, or it can be present in the form of solid. So when we talk about liquid, we can say that rainfall is nothing but an example of liquid, and at the same time solid means we can say snow, or we can call it as hail also. So these are the different types in which the water exists in the atmosphere. But what we want to know is how the water circulates inside in the atmosphere, and this phenomena is called as atmospheric circulation. So if we understood what is atmospheric circulation, we can understand that how water is transferring from one phase to another. So let us look at this small diagram where at the center we talk about atmospheric circulation. So from where do we get the water? So let us say there is a water body present somewhere along the ground surface. We call it ocean. So from the ocean, what happens? Due to heat energy which we receive from the sun, water starts evaporating. So evaporation happens from a water surface, we are calling it as ocean. Then this evaporated water enters the atmospheric circulation, and what we get is precipitation. And how do we get precipitation? The evaporated water will travel at a certain height where the temperature will fall down and condensation will start taking place. When the condensation start taking place, there will be formation of cloud, and from there we'll get the precipitation, which again falls onto the land surface. So this entire process is nothing but it's called atmospheric circulation. It means how the water is circulating in the atmosphere. So if we know this, how water is circulating inside the circulation in this process, then in the previous class we have talked about Reynolds transfer theorem. So what is the basic equation of Reynolds transfer theorem? We say that rate of change of any extensive property is equals to under control volume of the intensive property plus double integral of control surface of that internal property. So let us say we want to derive this equation, but we want to derive this equation only for the atmospheric circulation part. So what we are going to do, we are going to assume the extensive property, which is B, as mass of water. Let us say whatever mass of water vapor is present in the atmosphere, we are taking it as extensive property. So what will be the internal property? So the intensive property beta is nothing but dB by dm. So if we look at this, dB is nothing but it is mass of water vapor, and dm is nothing but mass of fluid. So that if we look at this definition, mass of water vapor upon mass of fluid, this is nothing but this is specific humidity. So here we can say that beta is nothing but QV, and what is QV? QV is nothing but specific humidity. From the definition here, from the formula here, we got that this is nothing but specific humidity. So we can say that here in the equation which we have already derived, equation 1 in Reynolds transfer theorem in the previous class, here what we can do is instead of beta we can write QV. Here also we can write QV. So this changes our equation. And also if we look at on the left hand side, dB by dt, so here also we have to make the change. So this dB by dt will become how much amount of water vapor is transferring. So we are calling it as mv dash, and mv dash is nothing but d by dt, and we are going to replace this equation 1 with beta as QV, rho a of dV plus double integral of QV rho a of V bar into d. So we have changed the equation 1 Reynolds transfer theorem along the atmosphere, and we have got a new equation. But the important thing to remember here is the mass of water vapor, it can be added into the atmospheric circulation or it can be removed. So when it is added, the process is called evaporation, and when it is subtracted, it is called condensation. Here from the diagram we can see evaporation is the process by which the water gets added to the atmospheric circulation, and condensation is the process from where the water gets removed from the atmospheric circulation. So this is the key word here. This we should remember. I think this can be asked in the examination as well. Like evaporation is what kind of phenomena it is. So we can say that it is a process from which water or vapor enters into the circulation. So this is like more about atmospheric water or atmospheric circulation. So this is like the first part of our session today. So the next important thing is vapor pressure. We need to learn about vapor pressure now. So what do you mean by vapor pressure? So if we talk about, just a second. So the simplest definition of vapor pressure would be the pressure exerted by vapor in the pressure exerted by vapor in the atmosphere. So it is denoted by E. So we can say that E is nothing but the pressure exerted by moisture present in the atmosphere. So we know there is certain water which is always there in the atmosphere. So whatever pressure is exerted by that moisture in the atmosphere, we call it as vapor pressure E. And the basic equation that we can use to define E is nothing but ideal gas law, which we have studied in our basic class 1 and class 2. So E is nothing but rho RT, and this rho R is nothing but, this is for vapor pressure, so we call it as rho V, RV and T. So we should know what these terms are. So here in this equation, rho V is nothing but the density of vapor pressure. The density of water vapor, we can say. Here RV is nothing but gas constant, and T is nothing but temperature, but we should remember here the temperature is in Kelvin. So this is the first definition which we would like to cover. This is nothing but, it's called vapor pressure. Now let us say we want to know what is total amount of moisture present in the atmosphere. We want to know total moisture present in the atmosphere. So we can say that the total moisture present in the atmosphere is nothing but we are talking about total moisture in terms of density. So it can be density of air is equal to density of dry air plus density of vapor. So this is nothing but the total moisture present in the atmosphere in the form of density. So if we can talk this in terms of pressure as well, so this will be pressure is equals to dry pressure plus vapor pressure. So we know that rho of A is nothing but rho of D plus rho of V, and similarly we can say that P of A is nothing but P of D plus P of V. So similarly we can write an equation for P of D. So P of D will be equal to rho D into RD into T, and we have the equation of PD now. So what we can do, we know that we don't have an equation for RD, like we know RV is nothing but gas constant, but for RD we have a relation between RD and RV, and what this relation is, that RV is nothing but RD upon 0.62. This equation is used to get your gas constant for a dry air. So we know the gas constant for moist air, we want to know it for dry air, so we can use this equation and we can get the value of RD from here. Now what we are supposed to do, we need to find an equation for P of air. So we are going to substitute here in this equation. Let us say this equation is equation 2 and this equation is equation 3. So we are going to substitute PD as rho D RD of T. So we will write this as PD plus rho D RD of T, and we can write this equation as in terms of density now, that rho D is equals to rho V upon 0.62 in terms of RD and T. Now why we are doing all these things? Because we want to know an equation for specific humidity. We have derived before the formula of specific humidity. What is specific humidity? Is nothing but mass of water vapor divided by mass of fluid. So you want to get an equation so that if we have some numerical problem with it and where we are supposed to get specific humidity, we can use that equation. So that equation could be QV, which is nothing but specific humidity. So QV is nothing but 0.622 into E upon P, where E is vapor pressure and P is atmospheric air pressure. So if we know vapor pressure and atmospheric pressure, using this equation we can get specific humidity. So this is first derivation which we wanted today about specific humidity. So whenever we find a numerical where they have asked us to calculate specific humidity, we can use this equation 0.622 into vapor pressure divided by atmospheric pressure. Now let us talk about saturated vapor pressure. What is saturated vapor pressure? We know what is vapor pressure. Now we want to study about what is saturated vapor pressure. So the symbol we can use is E of sat or E of S, anything which we want. Let us say the vapor pressure of, like at a given temperature, the vapor pressure of moist air containing maximum amount of moisture it can hold is called saturated. This means saturated vapor pressure is nothing but at any given temperature, the capacity of atmosphere to hold maximum moisture content is called saturated vapor pressure. So at any given time or at any given temperature, the maximum amount of moisture it can hold is called E of sat. So the maximum holding capacity of a water vapor is called saturated vapor pressure. So similarly for saturated vapor pressure also we have an equation. So E of sat is nothing but 611 times of exponential of 17.27 of temperature divided by 237.3 plus of temperature. So this is the equation from where we can find saturated vapor pressure. So now that we know what is vapor pressure and now we know what is saturated vapor pressure, so if we divide these two terms, we'll get a new definition, and that definition is nothing but relative humidity. So relative humidity is nothing but E upon E sat, means vapor pressure divided by saturated vapor pressure. So we'll get relative humidity and we can denote it as RH. So this is relative humidity. Now the next term is dew point temperature. Now for this we can use a graph as well. Here along the x-axis we'll get a temperature, and along the x-axis, y-axis will get saturated vapor pressure. So what does dew point temperature give us? So with the help of dew point temperature we'll get to know that at any temperature, let us say the graph is something like this. So at any temperature, let us say TD, where the vapor pressure becomes saturated, is called dew point temperature. It means where E will become E sat. When E will become E sat, we can say that point is called dew point temperature. So the temperature where E is equals to E sat, then we can say that T becomes TD. So we should remember this. When E becomes E saturated, that temperature is called dew point temperature. So the temperature at which vapor pressure becomes saturated vapor pressure is called dew point temperature. So these were the 5 definitions that we wanted to cover in the first session. So we studied about what is atmospheric water, how atmospheric circulation takes place. Then we talked about Reynolds transport theorem for specific humidity. We covered the definition of vapor pressure till now. We talked about saturated vapor pressure. We have covered relative humidity and dew point temperature. Now we would like to explore the relation between pressure and altitude and temperature and altitude. So for this, we can cover this under a concept called water vapor in a static atmospheric column. So what we are going to do, we are going to use two basic properties which we have studied in our previous classes. Let us say we have studied this equation which is called as ideal gas law. We already know this. So from ideal gas law, pressure is nothing but density of air multiplied by Ra of T. Let us say this equation is 1. And we also know about hydrostatic pressure. We have studied this in fluid mechanics. So P is equals to rho g of H. So using these two basic equations, we can derive the relation between pressure and altitude. So let us say the pressure is really small, so we can name it as dP. So when pressure is very small, we can say that the height will also be very small, so we can name it as d of z. So d of z and dP means the pressure is very small, the head is also very small. So we are going to use this equation 1 and 2. So let us say the variation of temperature. So when we talk about temperature, the temperature is air temperature with altitude can be. So from the basic understanding, we know that as we go at a certain height, the temperature starts falling. So when we know when the altitude is increasing, the temperature is going to fall. So the relation that we can develop is dt by dz, means temperature with respect to altitude is going to decrease. And what is alpha? Alpha is nothing but lapse rate. Lapse rate means per degree Celsius change or degree Celsius change per kilometer. How much temperature is going to change per kilometer? That is defined by alpha. So let us name this equation as equation 3. Now we know that from here we can say that d of A is nothing but P upon Ra of T. So similarly, this term we can substitute here also in this equation. So let us name this equation as equation 4. Now when we substitute equation 4, dP by dz is equals to rho g upon Ra of T. And now what we are going to do, we are going to keep the terms at the same time, same part, like this is P. So we'll keep the P pressure term at the same time and head term at the same time. So dP by dP is equals to G of dz Ra of T. And what is dz? From the equation above, from equation 3, we know that dz is nothing but dz would be dt of minus alpha. This term will be dt of minus alpha. So again we can write this equation as dP of P is equals to G Ra of T into dt of minus alpha. Now we are integrating this this equation on both the sides, and we'll rearrange the thing. So if we are integrating on both the sides from 1 to 2, we'll get P2 by P1 equals to T2 by T1 whole raised to G divided by alpha of Ra. So this equation is nothing but it gives the relation between pressure and temperature. And similarly, there is one more equation which gives us the relation between temperature and altitude, which is T2 minus T1 upon Z2 minus Z1 is equals to minus alpha. So from here we can get T2. For T2 would be T1 minus alpha into bracket Z2 minus Z1. So this equation will give us the relation between pressure and altitude. So whenever there are problems where we are required to solve the relation between pressure and altitude and temperature and altitude, we can use these two equations. So now let's come to another topic which is called precipitable water. Precipitable water. So what is precipitable water? What do you mean by precipitable water? So precipitable water is nothing but the amount of moisture, in a atmospheric column. Amount of moisture in atmospheric column is nothing but precipitable water. So let us consider an element of height dz in a column of area A, and let us say we want to find its mass. So mass would be density into volume. So here density is nothing but density of air, and volume can be area multiplied by the height of column. So this is nothing but mass of air. At the same time, if you want to find the mass of water, so what can be the mass of water? It would be volume multiplied by density of air multiplied by QV. And what is QV? QV is specific humidity. Now we want to find the total mass. So what we can do, we can integrate this term. So we'll integrate this term from Z1 to Z2 of QV rho A into dz. So why we are doing this? Let us say if we look at this with example of a numerical. So in numerical there can be we are supposed to find at different elevations specific humidity at different elevation, or we need to find the density of air at different elevation. So in that case what we can do, we can take average of specific humidity at one height plus average of specific humidity at two height. So what we can do is we can simply take the average of specific humidity calculated at different height, and similarly we can do it for density of air also. So how we are going to find QV1? So we should know the equation of QV1 by now. It is 0.622 of E1 by P1, and QV2 will be 0.62 of E2 by P2. So it means we need to we first need to calculate the vapor pressure and atmospheric pressure at those two elevations. If we know that, then we can calculate QV1 and QV2. And similarly for density at A, we can calculate it by using ideal gas law equation, which is P1 upon RA of T1, and similarly for QV2 it will rho A2 it will be P2 upon RA of T2. Then we can calculate this and we can get the answer for precipitable, like what is the total mass of water that is present in the atmospheric column. So this is all about precipitable water. So now we know that there is certain amount of moisture that is available there in the atmospheric column. So it means precipitation can take place. So we can now cover about precipitation. What is precipitation? And how does the precipitation form? So we should also talk about formation of precipitation. So how does a precipitation forms? So to understand that, the precipitation will forms in order for a precipitation to form, we can divide the process into two parts. The first part is called lifting of air mass. Lifting of air mass means like evaporation has just started and the vapor pressure is traveling towards is traveling to the atmosphere, is traveling into the atmosphere. And the next part is called nucleation. So nucleation means where the condensation before the condensation begins, that part is called nucleation. So we can cover the formation of precipitation in these two parts, like lifting of air mass and nucleation. So now how does an air mass is lifting? So to understand that, there are three different process under which it can happen. The first process is called frontal lifting. The second process is called orographic lifting. And the last one is called convective lifting. So what happens in frontal lifting is that, let us say there are two different types of air masses. One is called warm air, one is a warm air, and other is hot air, or you can say cold air. So when these two types of air masses you can say interact with each other, the process that takes place is called frontal lifting, and this can be take place under two heads. One is called warm frontal lifting and another is called cold frontal lifting, which means when these two particles collide and if warm air moves up, we can say that it is called as warm frontal lifting. And similarly, if when these two particles interact and if, let us say, cold air moves up, then we can say that it is a cold front lifting. So this is the first way where we can say there is a difference in temperature between the air masses, and because of that lifting is occurring, we can say that it is called as frontal lifting. In the another way, there is called orographic lifting. Like this type of lifting will mostly occurs in hilly areas. And how does that happen? Let us say there is a mountain somewhere near and the wind is blowing in this direction. So what will happen? Because this is the windward side, we can say the air will be hotter somewhere here along the surface, and when it moves above the hill, it will become warmer. So here it is hotter and here at the top of the surface it is warmer. So we'll say that here the condensation will start taking place and precipitation begins. So we can say that here we can receive rainfall. But here at the leeward side there will be no rainfall. So this is happening because of difference in elevation. So this kind of process is called orographic lifting. So this is first one, frontal lifting, is because difference in pressure, this is difference in elevation. Now the last one is convective lifting. What happens in convective lifting? There is difference in temperature, and this difference in temperature is due to height. So because of this the lifting will take place, and this type of lifting is called convective lifting. So there are three different processes: frontal, orographic and convective lifting. So either of the three processes will be the reason because of which the lifting of air masses is taking place. So when the amount of water is lifted up, the next part is nucleation. So what happens in nucleation, let us see. So the nucleation is nothing but condensation of water vapor on tiny particles, and these tiny particles are called aerosols. So these aerosols could be dust particles that are present in the air, so nucleation, we know what is nucleation, is nothing but the process where condensation is happening. and this condensation is happening how the water vapor is carrying is moved up along with the tiny particles called aerosols, which are already present in the atmosphere. So there is a good what you can say, we have a good schematic diagram as well. If you look at the notes that have been uploaded in the portal, you will find a good presentation where they have explained like how lifting of air mass is happening. Then initially the particle will be small in size, but as it is moving up in the atmosphere, the particles in size increases. Why is it is increasing? Along because of aerosols. Now what happens? Now again it will move up and the particle will start increasing in size. And what happens is they droplet will become that heavy that it won't be able to hold the water inside it, and at that moment will receive precipitation, and again the cycle keeps on repeating. The precipitation will form and again the evaporation will take place and again the process will repeat. So there is a good diagram from which you can easily understand the entire process, like how formation of precipitation is taking place. Now the next part is to see what is terminal velocity, and this is the last part that is there in the second module. So terminal velocity, we are already familiar with this term. We have studied this in our basic class 1, like +1 and +2 junior college physics. We have studied this. So what is terminal velocity? So what happens in terminal velocity is when we drop any certain particle from a certain height inside a liquid column, what happens is after a certain point of time, its velocity remains constant, and that constant velocity is nothing but terminal velocity. So this we have already studied, but this we have studied for a metal body. But now we are going to talk about in terms of liquid. So let us say we are talking about a raindrop. So let us say there is a spherical raindrop which is falling. Why it is falling? Because of gravitational force, and there are two different types of forces which is going to oppose this. What are those two forces? The first force is buoyant force and the other force is drag force, right? If it is falling inside a liquid column, there would be some liquid already present in the system, so there will be certain friction, and because of that drag force will come into picture. So we can say that the gravitational force is balanced by buoyant force and drag force. So we need to know like what are the equation for each of this term. So this is force. Force means what? How you can derive force? So we can write simply the equation for Fg. Fg is nothing but density of water multiplied by volume. Volume of sphere is pi/6 of du cube. So this is nothing but gravitational force. And similarly we can find buoyant force, and buoyant force is nothing but due to air. So we can write the same equation in terms of air. So rho A of G multiplied by pi/6 of d cube plus drag force. So in drag force we know the equation for drag force, that is drag coefficient multiplied by rho A into pi/4 of area into V square. Into A into V square by 2. Now let us arrange this term and find the equation for V. So how we can find the equation for V? We'll take this term of buoyant force to the left hand side. So the equation would be rho w of g into pi by 6 of dq minus rho of air into g into pi by 6 of dq equals to cd into rho a into area. So area would be pi by 4 of t square into v square by 2. So now if we solve this equation for v, we'll get the equation as 4 by 3 of small g into d upon cd multiply by density of water upon density of air minus 1 raised to 1 by 2. So this is the final equation for terminal velocity. We can call it as Vt. So if you want to have a look into the detailed derivation, so you already have the PDF for that. So if you want to know the detailed derivation of this, you can look into it into the PDF as well. So now here the key point is why we have taken the raindrop as sphere and up to what diameter can we take the raindrop as sphere. So we should know that we can take the raindrop as spherical until its diameter is 1 mm. If it is above 1 mm, we have to consider it as oval. Right? So this is all about the theoretical aspect of the module 2. So what we have covered till now is we have covered atmospheric water. What is atmospheric water? Then we have studied the process called atmospheric circulation, which tell us about how the water vapor is the water is circulating in the atmosphere. Then we talked about specific humidity. So specific humidity, we know the notation so far, it's QV, and what is specific humidity is? It is mass of vapor divided by mass of water, and we can use the equation as 0.622 into vapor pressure divided by atmospheric pressure. Then we have talked about what is vapor pressure, small e, and we know that the pressure exerted by the moisture in the atmosphere is nothing but vapor pressure, small e. Then we talked about saturated vapor pressure. What is saturated vapor pressure? Saturated vapor pressure is nothing but the maximum amount of moisture that can be held is nothing but this called saturated vapor pressure. It is denoted by E of sat, and we know there is a huge big equation to calculate E of sat, which is 611 into exponential of 17.27 of t upon 237.3 plus t. So using this equation we can calculate E sat, and we know what is E. Once we know these two definitions, we can calculate another term which is called as relative humidity. So relative humidity is nothing but E upon E sat. And lastly we covered dew point temperature. So what is dew point temperature? The easiest way to remember dew point temperature is at any temperature when vapor pressure becomes saturated vapor pressure, so that temperature is nothing but dew point temperature. So we have covered this first part. Then we have derived two relations, the relation of pressure versus altitude and also temperature versus altitude, where we got to know that as altitude increases, pressure decreases, and similarly as altitude increases, temperature decreases. So we have got an equations for both of this. That equation is P2 by is equals to P1 T2 by T1 whole raised to G divided by alpha of Ra, and T2 is equals to T1 minus alpha Z2 minus alpha. Here we need to remember the graph as well. When we talk about this graph, Like this is altitude Z and this is pressure P, this is altitude Z, this is temperature T. Here the relation between pressure and altitude is not linear, it is non-linear, whereas the relation between pressure and temperature is linear. So we know the relationship also. Here the relationship is non-linear, here the relationship is linear. I think it can be asked in terms of MCQ as well, that what is the relationship between pressure and altitude. So we should remember the graph. If you look at the graph, you can easily say that it is non-linear and here the relationship is linear. Then we talked about formation of precipitation. How precipitation is formed. So we know that precipitation is formed under two processes. First is lifting of air mass and the other is nucleation. So lifting of air mass is again further divided into three heads we know. First is frontal lifting, orographic lifting and convective lifting. So frontal lifting happens because of difference in temperature. This happens because of difference in elevation, and this happens because of difference in temperature as well as elevation. And what is nucleation? Nucleation is nothing but condensation. And we have understood this with the help of a graph as well. The last part that we covered was terminal velocity. So we have covered all the theoretical aspect of the module 2. So now what we are going to do is we are going to solve few examples based on few of this topic. So we are going to solve few of example. So I'll give you few questions for that.